here, our goal is to solve a problem involving both series and parallel resistors. So our first order of business here for this problem is to find the total resistance of this circuit. That's the same thing as saying I want to find the equivalent resistance of this circuit. When I ask for the equivalent resistance, that's essentially finding the total resistance of this whole thing. I could take all of these resistors out and replace them with one resistor that has that equivalent resistance, same resistance. That's what it means when I'm asking for an equivalent resistance, or even equivalent capacitance when we were talking about that earlier. So, in order to find the total resistance of this combination of resistors, I have to break it up into a couple of different pieces. The first thing I'm going to do is I'm going to combine both of these resistors, which are in series, and also combine both of these resistors here, which are in parallel. Okay, and we're gonna combine those resistances and create a new diagram that represents this diagram, but we've combined these two in series and these two in parallel. Okay, so I'm going to call the resistance, the total resistance of these two in series, I'm going to call that R12. Okay, so since these are in series, when we're in series, our resistances just add up. So the total resistance of these two in series will just be R1 plus R2. So that will be 8 ohms plus 4 ohms, and that will give us a resistance of 12 ohms. Okay, for these two in parallel, I'm going to call that R34. Okay, when our resistances are in parallel, they combine together using this inverse relationship. So I can say 1 over the combination of these two in parallel equals 1 over R3 plus 1 over R4. So this is the same thing as saying R34 is equal to 1 over R3 plus 1 over R4 to the minus 1, or the inverse. We take the inverse of both sides. 1 over 1 divided by R3 gives us back R3. And then 1 divided by this whole combination here, we can write that as the inverse of 1 over R3 plus 1 over R4. We can write it like this. Okay, so this is equal to 1 over 6 ohms plus 1 over 3 ohms, all to the minus 1, the inverse of that. And that gives us a resistance of 2 ohms. Okay, so we see that when our resistors are in series, they add to be, the total resistance adds to be greater than any of these two on their own. And then when our resistances are in parallel, they combine to be less than the resistances of any of these two on their own. So I can replace these two resistors in parallel with one resistor that has a resistance of 12 ohms. I'll call this R12. And I can replace these two resistors with a resistance of 2 ohms, a resistor that has a resistance of 2 ohms. So I'll call this R34, and that resistance is 2 ohms. So now these two combined together are in series with each other. So if I add these two in series, when we're in series, the resistances add. So our total resistance will be the resistance of this one, which I called 1, 2, plus the resistance of this one, which I call 3, 4. So that total resistance will be 12 ohms plus 2 ohms, and that will give us 14 ohms. Okay, so the total resistance of this combination of resistors is 14 ohms. Previously, we combined our resistors together to create this set of resistors, and then I combined these two in series to create the total resistance of this combination of resistors. So we combined and we made a couple of new diagrams that all represent the same circuit here. And then I went ahead and I drew a chart or a table over here to keep track of some of my values. So resistor 1 has a resistance of 8 ohms, R2, 4 ohms, R3, 6 ohms, R4, 3 ohms. Our combination of these two resistors gave us 12 ohms. Our combination of these two resistors gave us 2 ohms here. And then our combination of all the resistors together gave us a total resistance of 14 ohms. And now our task is to find the current through each one of these 4 resistors. So I want to find the current through resistors 1, 2, 3, and 4. The currents might not necessarily be the same through all of them because these two are in parallel, so the current had to split. The current is coming through these two resistors in series, and then my current has to split between this top resistor and this bottom resistor. So all of these are not going to have the same current, and we need to figure out what that current is. We might as well find the potential across all of these resistors as well. Now, in order to do that, we're going to start with our total resistance here and use that to find what is my total current. And then we'll use some of the rules for our resistors in series and parallel. Then let's first find the total current in our circuit. Remember Ohm's law, V is equal to IR. So if I solve that for I, the total current will give me, the total current will equal our total potential divided by our total resistance. Okay, and that will be our total current running through the circuit. Oh, what I didn't tell you, we have to connect this combination of resistors to a battery in order to supply a current. So let's connect this combination of resistors to a 42-volt battery. So the total potential of my circuit here will be 42 volts, okay? So I know the total resistance in my current is 14 ohms. I know the total potential supplied by my battery is 42 volts. So I can use that to find the total current in my circuit. So that total current will be our 42 volts divided by our 14 ohms of the total resistance, and that gives us a total current of 3 amperes. Okay, so my total current here is 3 amperes. Okay, so let's look here in this step where I drew my kind of equivalent circuit diagram. The combination of these two resistors in series, which I called R12, the combination of these two resistors in parallel, which I called R34, these are in series with each other. Okay, and when we are in series, our current running through those equivalent resistors is the same. So this equivalent resistor R12 has a current of also 3 amperes running through it. And our equivalent resistor R34 also has a current of 3 amperes running through it. Now, since R12 is made up of a combination of resistor 1 and resistor 2 in series, where resistors in series have the same current, so that means that resistor 1 and resistor 2 have the same current through them as either of these two equivalent resistors here. So R1 and R2 both have a current also of 3 amperes. 3 amperes. Okay, so now we can figure out, we might as well go ahead and figure out what the potential is across these resistors. So in order to find the potential across a resistor, you use Ohm's law, V is equal to IR. So the potential across resistor 1 is the current through it times its resistance. So that will be 3 amperes times its resistance of 8 ohms, and that gives us a potential of 24 volts, okay, across resistor 1. And across resistor 2, we do the same thing. V2 is equal to I2R2. So the current running through resistor 2 here is also our 3 amperes. And the resistance of resistor 2 is 4 ohms. And that gives us a potential across resistor 2 of 3 times 4, that's 12 volts. 12 volts here. Okay? So these two in series, when we've got our resistors in series, the potential across them adds. For resistor 1 and resistor 2, the potential will add across them. So the potential across this equivalent resistor, R12, is the sum of the potential for resistor 1 and resistor 2. And so the potential across our equivalent resistor here, R12, is going to be the sum of the potential across resistor 1 and resistor 2. And so that will be 24 volts plus 12 volts, and that will give us 36 volts. Okay, so if I came in here with my voltmeter, I want to measure the potential across here, I would get 36 volts. That would be the same as if I put my probes here and here, and I found the potential across here. That would also give me 36 volts. Well, now let's think about resistors 3 and 4 here. Okay, we don't have their current or their potential yet. Well, let's see. We know that when resistors add in series, their potential adds. So the voltage or the potential drop across resistor 1, 2 here, plus the voltage drop across my equivalent resistor 3, 4 here, has to equal the total potential supplied by our battery. So this has to equal V, which was the potential supplied by our battery. We already know what the potential is across this resistor here, R12. So we can solve this for the potential across this equivalent resistor here, R34. So the potential across that resistor will be the total potential supplied by our battery minus the potential across resistors 1, 2 in combination. So this will equal the potential supplied by my battery is 42 volts minus the potential across my resistor 1 and 2 in combination, which is 36 volts. That means that my potential across resistor 3, 4 here is 42 volts minus 36 volts, or 6 volts. So over here, my resistor 3, 4 has 3 amperes of current, and it will have a potential of 6 volts. Now you could also find this by using V is equal to IR for that resistor. If V is equal to IR, we already know the current through this equivalent resistor. We already know its total resistance here, so 3 times 2 would give me 6 volts. And then if I came in here with my voltmeter and measured right here, I would find a potential of 6 volts. And since these are in series, 36 plus 6 should add to give me my total potential supplied by my battery, which is 42 volts, and it does. Okay, so we have these two resistors yet to fill in their slots. All right, so this will be our final step to get the potential and current through all of these bits of our circuit. Now, when our resistors are in parallel, they have the same potential across them. So if my combination of resistors 3 and 4 here, my equivalent resistance for these two, has a potential of 6 volts across it, that means that both of these resistors, since they're in parallel, will also have a potential of 6 volts across them too. So the potential across resistor 3 will equal the potential across resistor 4 will equal the potential across my resistor, which is the combination of 3 and 4, and that's 6 volts for all of those. So over here, we're running out of ink. Resistor 3 and resistor 4 both have 6 volts of potential across them. So if I came in here with my voltmeter and I measured here and here, and I measured here and here, I would get 6 volts for each of those. Okay, and then I can find the current running through each of them by saying that, let's see, already we rearranged Ohm's law to solve for I. So I3 will equal V3 over R3. So that will be 6 volts divided by the resistance of R3 is 6 ohms. So I3, the current running through resistor 3, is 1 ampere. 1 ampere. Now if I do the same thing for this fourth resistor, if I do, running out of room here, I4 is equal to V4 over R4. Okay, that's equal to the potential across resistor 4 was 6 volts, divided by the resistance of resistor 4, which is 3 ohms, and that gives me a current of 2 amperes through resistor 4. 2 amperes. Okay, now, we also see that the current through parallel circuits must add to give you the total current. So the total current that was coming in through here was 3 amperes. It has to split that current to run through this top resistor and to run through the bottom resistor. So the current through my top resistor here, that's my resistor 3, was 1 ampere. The current through my bottom resistor here was 2 amperes. So 2 amperes plus 1 ampere gives me 3 amperes. So we are satisfying all of these rules for series and parallel circuits within our circuit analysis here. So when you're presented with a circuit analysis problem, maybe I gave you this problem and I asked you to find the current through resistor 4. Okay. Probably the best way to approach that problem is to create a table like this. You've got all of your resistors and your equivalent resistors here. You've got the total resistance. And then you find the current and the potential across each of those elements. You have to break it down and solve it a little bit like a puzzle, using also our rules for series and parallel circuits in order to get at the current or the potential across any of these individual resistors.